I think that one of the things that makes this culture work for geotechnical engineers is I have some experience from marine geology when I first started working at the U.S. Geological Survey years ago. And a really positive culture would develop in a group that went out to sea, that had to be a cohesive group and went out for 4 weeks out into the Pacific to do a geophysical survey. You really were on your best behavior to get along because you had another 3 weeks to sit down across the table and have a meal with that person, right? So you did what you could to get along with people. And I think what happens with geotechnical engineers in the field is similar. We're inclined to work together because we spend so much time in the field in sort of our day-to-day analysis of problems. So I'm going to talk about the consequences of good reconnaissance investigations. Much of what I'm going to talk about is in the GEER manual. So if you look to, I think, something like page 15 or so in this booklet, there's a GEER manual that will lay out a lot of the core elements of what we're going to talk about today. And you'll see the ideas in this GEER manual woven through the talks in the morning, the field exercise in the afternoon, and so on. So you can come back to here as a reference. The most important thing when we have a group go out into the field is to develop a culture of safety. So we really don't want to have anyone in the reconnaissance get hurt or not come back with a very positive experience with the data collection. So that's probably the most important thing, I would say. With regard to your question about how are people picked for the reconnaissance, I guess the one thing that I would add to that is that we have domestic and international events. And when we have an international event, we have just so much funding, and we're constrained in a budget sense of how we field an operation. On the other hand, for example, if we have a local domestic event, it's essentially free expertise that wants to participate, and we're thrilled to have that expertise participate. So you might have, for example, a small earthquake like the Napa earthquake that occurred a month and a half ago, and a much larger team investigating that than we would have investigating the magnitude 9 Tohoku earthquake in Japan, right, which is affecting 600 kilometers of coastline. So we have that disconnect, and it has much to do with where the earthquake happens. Anyway, refer to this manual as we go through the day. So, like many of you, I've participated in many reconnaissance investigations over the last 20 some odd years, and also, particularly those of you who worked on master's or PhD theses, you've been the users of these products. So you have gone into these old reports and you've tried to extract useful information to help you develop a capability, a new capability, right? So at the time that you are holding this 1964 Niigata report, right, techniques didn't even exist that you're investigating, right? Computational methods, the ability to capture data in a very sophisticated way relative to what was done in 1964. So I've been on the other end of trying to develop a new data set. So in my case, I'm interested in the shear wave velocity of liquefied ground. I'm interested in the shear wave velocity of ground, period. And I use surface wave methods. Great. Well, at the time that most of the reconnaissance reports were written that I needed to capture data for, those methods didn't even exist, right? So what was it that made one report a good report and another report not so good, right? In this study of collecting a global data set of liquefaction observations using surface waves, I've looked at, I don't know, something like 3 score core reconnaissance reports that we needed to actually get to sites on the ground to try to relocate on the same site and capture data. So I want to tell you what I've learned in the investigation of these sites and reading all these reconnaissance reports. In this study, to populate this correlation on the right, we went to 4 continents, 27 earthquakes, 5 countries, and basically I would drive around Japan or China or Taiwan or Alaska with a library in the car. We would have all the reconnaissance reports with us, and we would try to mine those reconnaissance reports to arrive back on those sites. Most important thing about a good reconnaissance report is that everything is geolocated. If you have an observation and it's not placed on a map, or we don't have a latitude and longitude, it's not a very useful observation. So if we have good maps, we can return to sites like the front cover of Geotechnical Earthquake Engineering, Steve Kramer's book. We can return to those sites and locate right on the same sites, same location, and collect our data set today. So all other aspects of those reconnaissance reports aside, the ability to locate is key. Secondary questions turn out to be very important in reconnaissance reports. Sort of feathering to what John said, where, well, sometimes you get people on a reconnaissance who just want to see the big damage, right? Damage tourism. That's not what we want to have on a GEER reconnaissance. Actually, what we want to do is we want to find where things are interesting in geotechnical engineering, and where things are interesting are on the boundaries of failure and non-failure, collapse or standing structures. So why did damage not occur at a location? That's kind of critical. You go to a site and you're driving past areas of no damage, not recording anything, waiting until you see damage. That's sort of the classic mindset of a reconnaissance. But in a GEER reconnaissance, we want you to be saying, this neighborhood has no damage. We need to investigate why this neighborhood is fine, but that neighborhood across the highway is whacked. Why do we not have observations of damage in certain locations? If we're looking for the threshold of failure, we're looking for minor damage. We're looking for where things start to fall apart. We're getting low levels of strain. So if we're really focusing our energies right, we're not looking at the 2-meter, 10-meter lateral spreads, but we're looking at where things are starting to fall about in the decimeter scale. That's where the boundary is occurring. And secondly, or I would say thirdly, what this aspect again of reoccupation of sites. So here's a big problem that I saw in a lot of old reconnaissance reports. You might be using the Taiwan datum of 1956 in this old report, and you're using a GPS unit with WGS84, and you can't locate on the site because they're offset from one another by something like 300 meters. And if you can't extract the modern latitude, longitude, useful world geodetic coordinate system values, you're going to have a problem locating on sites. So it's really important that we standardize on how we locate our data sets here and other places on the other side of the world. And there are ways to do that. So good reconnaissance reports don't just have the text describing what's occurred there, but they have lots of maps, lots of photographs, really useful things. So one of the best reconnaissance reports is one of the earliest ones we used. In 1948, just after World War II, there was a disastrous earthquake in Fukui, Japan, on the Japan Sea coast, that the it was called the Far East Engineering Command. It was the sort of predecessor to the Army Corps of Engineers in the Pacific. And they did fantastic aerial surveys of liquefaction damage all throughout Fukui. So some of the best products that were developed using these great airborne data sets were from Hamada, from Waseda University. And so here's an example next to the Yoshino River. This is in the Morita-cho neighborhood in Fukui, where you can see rice fields before the earthquake, 1945, and then rice fields again after the earthquake. And you can very clearly see where there are sand boils on the surface and lateral spreading. And so when we went to reoccupy those sites, we found some very interesting things. There are a lot of houses built in these neighborhoods now. They're not rice fields anymore. It's become somewhat urbanized. But what you can see is that the house grid, this is on a JAF, this is like AAA in Japan, Japan Auto Federation, map, and the street grid is the rice field grid. And so where you see liquefaction occurring in the rice fields, you can locate in an urban environment, in a park, and know that there were observations of liquefaction that occurred there. This wouldn't have been possible if we didn't have good aerial photographs, and we didn't have someone like Hamada do the scholarship to try to pull together these observations in a modern report that we could then use as a roadmap to get us to these sites. So here again, we're in Morita-cho doing our surface wave tests at a site that we couldn't have gotten to without Hamada. There are maps, and then there are maps. First off, what do you need for a map? You need to have a north arrow or direction. You need to have latitude and longitude. You need to have a scale. Okay? If you don't have those things, it's not a map. A graphic scale, yeah. Yeah. Thank you. Another map, fetishist. Right. So this is an example of a graphic, and I'm not even sure that it's a map by that definition, but basically what we see over and over again in reconnaissance reports is that the best maps have multiple overlays of data and information that allow you to correlate one type of damage to a building stock or geology or topography, so on. So that just having a map of damage aspects really doesn't cut it. So when you're out in a reconnaissance, be thinking about multiple layers of information that you could have in one source. So here's a very famous Menard map of Napoleon's march to Moscow, how disastrous it was. And there are 7 layers of information on this map: the army size, the events, the direction, location, stops, temperature, and then, of course, basically something like latitude and longitude, where they actually marched. Pretty useful map. One map like that's worth a book. So here's a modern reconnaissance report attempt at trying to do the same sort of thing. This is Ellen Rathje's study of the damage in Haiti, where she's tried to overlay the building stock. You can see where it's dense and where it's not dense. Grades of damage in that building stock, color-coded. The geology. So we have, again, multiple layers of information telling you where it's urban, where it's rural, where the damage occurred, and how that damage intersects with the underlying geology. This is, Scott Ashford and I did a study of the 2003 Tohoku earthquake and magnitude 8 earthquake. And this is the same kind of idea of trying to overlay multiple types of damage into one map. Where here we're trying to overlay the epicenters, the damage areas, the PGAs, the tsunami run-up heights are down here on the bottom scale, where there were ground failures, landslides, structural damage, liquefaction damage, and lifeline damage. So basically, in one map, you would have a sense of where damage occurred spatially across the island of Hokkaido. So these are examples of maps that have multiple layers of information that we just find to be useful things. Hamada was really fantastic in putting together these paper reports in the 1980s and 1990s. So here's some examples where he had cross-section products that today would look quite simplistic, but at that time they were really revolutionary in reconnaissance reports. For people to be thinking in reconnaissance, gee, what does the cross-section through the geology look like at this site, right? And then he also was very, very keen on plotting displacement vectors. So here, for example, is this famous Ogata school in Niigata, Japan, and so he went through all these reports and basically generated a more modern reconnaissance report, the basic information for this old earthquake based on the aerial photos that he had. So this is a man that's generating a reconnaissance report 20 years after the event. Kind of interesting. So his vector map and his cross-sections allow us to locate right on critical sites along the transect at the Ogata school to make our measurements with a method that didn't exist at the time he was working on his reconnaissance report. And this is an example through just the last year this is the Cox et al. And Tokimatsu and Katsumata reports for the Tohoku earthquake of 2011. So these are recent EERI products. And basically what we have in these reports are good cross-sections with geology, very similar to Hamada. And then we have maps that are showing the geology, the age of the various fills, the degree to which liquefaction occurred, where strong motion instrumentation was located in or out of liquefied ground areas. So again, multiple layers of information on one map. So I think the lessons from Hamada are the following: that you try to maximize your use of photographs, particularly air photos if they're available. Google Earth today is really a fantastic tool. And in Google Earth, you actually have the ability to go back to prior data sets and look at before the event and after the event, and even look at damage from that perspective. Include well-drafted street-level maps and cross-sections if possible. And these can be augmented now with these modern data sets that allow us to get digital displacements using LiDAR or photogrammetric methods or so on. So here's sort of a modern example of that. This is from the Niigata Chuetsu Oki earthquake in 2007, I think. 2007? 2007. And so here are sites here that you see displayed in Google Earth. So in Google Earth, actually, I should just break out of this. Let's just go to Google Earth. And so this is the way that we're making a digital overlay of multiple damage aspects in an earthquake. So here are several hundred observations. If you zoom in, you'll see many more of these. The circles open up. This is just south of Niigata, Japan. And if you zoom in on these areas, you'll see these points. If you open up the Google Earth the KML, there we go. Here are the sites. And let's say after the reconnaissance, you're interested in strictly bridge bearing offsets. Well, that's where they are, right? You don't have to look all over this data set or through reconnaissance reports, they're right there. If your interest was in ground settlement sites, well, there they are, and so on. At each of these sites, if you went to them and you clicked on them, you would see the site ID. One of the things that we're going to do in this exercise in the afternoon is collect data, sort of a fictitious reconnaissance. So whatever the initials are of your name, it should be site AB1, right, or BC1. And then when you collect your next site data, it's BC2 and BC3, and they're all sequential. And of course, your photos are geotagging the location and the time, and your GPS is doing that. So this is the way that in the field in GEER, we have 10 people out collecting data set. We know who collected it by the site ID, and we know sequentially when it occurred during the reconnaissance. The next thing we have is a description of the damage that occurred at the site, the latitude and longitude, who took the photos, so BC's Brian Collins, what kind of damage aspect was noted at the site, sort of to check the box, liquefaction, ground settlement, structural settlement, severe structural damage. Any one of these sites, if you click on the image, and this internet connection works properly, ooh, maybe it just took me out. I'll just go, oh, I'll go back. Let's see. Huh. Oh, here we go. It has to go to the web, so it had to open up Safari. So if you click on any one of the thumbnail images, you get the full resolution data set available to you. So if you're interested in bridge bearing offsets, it's kind of a great tool for you to go back and investigate these sites. You very quickly get the data that you need. So this is an example of one of thousands of images that are stored, that are culled through, but over 10 different participants in this reconnaissance, their selected photographs are all available to you through Google Earth. So this is an example of a modern map. Okay, negative space. It's kind of a complicated thing because everything that you go through before you get to the damage zone is negative space, right? So it might be an earthquake up in the Japan Sea coast. You have to drive from Tokyo, so you've got about 4 hours of negative space. And suddenly you start to see things happening, you know, damage on a highway, small structural failure of an old building, and you know that you're at the periphery of the damage zone. And at that point, you really sort of have to have your eyes open for areas where damage is not occurring. So it's very important to be mindful of this. It's a hard thing to get yourself adjusted to looking for where damage has not occurred to where it has occurred. Also, good examples of reconnaissance reports in the back from the past. So this is Les Yao's report from the Hokkaido Nansai-Oki earthquake. This is up in the very southwest part of Hokkaido. And so Les doesn't have a GPS. He doesn't have anything but his film camera and his notebook. And he actually, Les Yao, he took pretty good notes. If you go to Les Yao and you ask him about, you know, what happened at that earthquake, he will reach back and he'll pull his yellow field notebook out and he'll flip and he'll tell you exactly what happened at that site. He was a very good note taker and a good photographer. So I think in some of these old reports, just good use of photographs that don't just look down at that lateral spread or liquefaction sand boil on the ground, but look also at the skyline and capture critical elements that help you locate on a site, that those are important things in a reconnaissance report. So here, for example, in Les's pictures, we have an embankment failure and basically a softening embankment. And you can see in the background that there's a structure, that there's a tall tower in purple, the structure is in green, there's a road sign, or actually one of these, in Japan they have these signs that are on top of embankments, just telling you what embankment it is. And so we could drive along this embankment, and we can see the sign, and we can see the tower, and we can see the house, and locate it just as it was in Les Yao's photograph, and know that we were on the site, and test it, right? So once again, the value of good photographic skills that capture the background as well as the topic of interest. Les wasn't thinking about that tower and that house and that sign. but it turned out that I needed his good skills at taking photographs to relocate on that site. Okay, I think that's it.